I guess we can start now. Okay. Welcome to the Computer Security Seminar at Purdue University. Our speaker today is Jintai Ding from the University of Cincinnati, and he will speak on internal perturbation of multivariate public key cryptosystems. Jintai.
Thank you. First, I would like to thank the organizer, especially Sam, for the opportunity to give this lecture here. The title of the lecture is called Internal Perturbation of Multivariable Public Key Cryptosystems, and I'm from University of Cincinnati. This lecture basically contains two parts. First, I'll give an introduction of cryptosystems. In particular, I introduce what is a Matsumoto-Imai system and what is linearization equation attack and their generalizations and so on. And then I'll present the second part of the talk, which is about internal perturbation. So introduction. So what is a multivariable public key cryptosystem? I assume here everybody knows what is a public key cryptosystem. And the most famous one, of course, is RSA. But RSA is based on a number theory principles and is used as a function of one variables. And the multivariable public key cryptosystems are cryptosystems based on functions with multiple variables instead of single variables. And let me give you a quick example. Okay, so in this case, the cipher is given as a function with n variables and mapped to a space with m components. Okay, and this is each component gi here are multivariable nonlinear polynomials. Okay, this is the public key, and any plain text is given as an element of a vector, and such that if you want to encrypt, you just calculate the value of this vector using this map. And to decrypt the ciphertext, you need to know some secret, which is basically the secret key, so that you can invert map to find the plain text. And then first, I want to present a toy example. So we'll use a finite field K, and this is a degree 2 extension over Z2. And then in this case, we have 4 elements. We'll denote these 4 elements just by 0, 1, 2, 3. Here, 0 represents 0, of course, and 1 represents 1. 2, however, stands for x, and 3 stands for 1 plus x. This is an example of a finite field. And one of the examples is given by the following. You have G0 with 3 variables, and G1, G2 as well, and they are quadratic polynomials. Okay? So suppose you have a message which x0 equal to 1, x1 equal to 2, and x2 equal to 3, which are elements of the finite field. You just calculate the value. You can see the ciphertext is going to be y0 equal to 1, y1 equal to 0, and y2 equal to 1. So basically, you have a message, and then you just put the message into the function and calculate the value. Okay? And this is a bijective map, which means we can invert it. And this is an example which we produce based on Matsumoto-Imai cryptosystem, which I'll explain later. Okay? What is the theoretical foundation in terms of security for such an idea? Okay? And it is the proven theorem which says that if you have randomly chosen n variable, n quadratic functions, quadratic equations, if you want to solve it, this problem in general is an NP hard problem. Okay? And why this is the foundation? Because when you attack the system, what you need to do is solve a set of quadratic equations. So if you can solve a set of quadratic easily, you can break all the systems. But we know, because it is NP hard, therefore we know it is very difficult to to break it using such a principle. Sorry. Okay. And another thing here I want to emphasize, if you notice that the functions we want to use in general are quadratic functions. Why so? Because you can see the public map are given by polynomials. And if you have a polynomial with n variable, if the degree high, the public key size will be too large. So in order to do things efficiently, you must what? make the degree as low as possible. Of course, you don't want to choose linear because linear equation can be solved easily. Okay, so therefore, you always want to build a quadratic system. Okay, and from mathematical point of view, also it makes sense because we know if you want to solve a polynomial equation, the degree high case is no different from degree lower case because we know every high degree polynomials can be reduced, polynomial equations can be reduced to quadratic equations by adding more variables. Okay, therefore, we always like to do quadratic maps. Okay, and the fundamental motivation to build such a system coming from two. The first one, of course, is to resist the quantum computer attack. So by now we know all the number theory-based problems can be what? Can be broken. A number theory-based crypto system can be broken easily if we have a quantum computer. And by this stage, we do not know, or we cannot show that quantum computer can help at this moment. Okay? And the second motivation is efficiency. We know ISA system at this stage, minimum requirement if you want to have a secure system is 1,000 bits. In this case, the computation is very large. That means we cannot use existing public crypto system for small devices, for example, RFID tags or sensor networks. So people are looking for things which are much more efficient. And in this case, if you use small finite fields, it seems to us that there's a great potential we can build a system which are much faster than ISA. Okay, so those are the motivations. And I want to give a short introduction of the history of the multivariable cryptosystems. The idea of multivariable cryptosystems first was suggested by Diffie and Fair. Okay, at the beginning of the 1980s, and even though they suggest the idea, but they could not realize it. And later, Shamir did some work, but Shamir's suggestion also did not work. It was broken very quickly. And the first substantial breakthrough was the system developed by two Japanese guys. Their names are Matsumoto and Imai. Okay, and then later it was broken, but however, Pataran picked it up. And Pataran and his research group did a tremendous work to produce new systems. And here I want to also mention one example, which is TTM, and this is a system invented by Professor T.T. Moore here at Purdue, even though all of them are broken. And now I also want to mention S-Flash. Okay, so last year in Europe, they take S-Flash, which is a Matsumoto Imai minor system. They accept it as a security standard for low-cost smart cards. And this is called a NISE program. It's a new European security standard. Okay, and this example is a multivariable proof system. And the name is also S-Flash. And you can see the motivation for this here is for low-cost smart cards, which means for small devices. And they are very fast. And now I want to give a quick introduction about Matsumoto Imai system. Okay, and let's first fix the notation. So I have a small finite field K, and which is characteristic 2, and the size of the field is Q. And then I do algebraic extension of this field, a degree n algebraic extension of this field, and I have a bigger field called K bar. Okay, and of course we know K bar can be identified with the n-dimensional K linear space, and I define this map phi and the phi inverse, which can transform back and forth. Okay, and their idea is very simple. Okay, and this proposal was done in this idea was proposed in 1988, and they proposed to use this map F, which is defined over the bigger field K bar. You map an element in the bigger field K bar to x to the q to the theta plus 1. Okay? The important thing of this is quadratic property. And so this is a map from bigger field K bar to K bar. And then we can compose phi and the phi inverse on both sides. Now it becomes a map from K to the n to the K to the n. And this map is quadratic. And you would ask me why it's quadratic, because you notice that x to the q to the theta plus 1, of course, is equal to x to the q to the theta times x. This is a linear map if you look at it in terms of smaller field. And this one is also a linear map. This is what we call the Frobenius map. Okay? So you have two linear maps, you cross them together, it produces what? A quadratic map. Okay? And then this poses a very interesting idea. Then you compose two invertible linear maps, L1 and L2, to hide this map. Okay? What L2 does is essentially change your basis. And what L1 does is mix the polynomial together. Okay? And this is it. This is the cipher. The F bar is the cipher. Okay? And now they impose the following condition, which is what? Q to the theta plus 1 is co-prime with respect to Q to the n minus 1. Because the finite field size is Q to the n, And the element of the non-zero element form a cyclic group. If we know if you raise the power, and if the power is co-prime with the size of the group, it is an invertible map. So that map is invertible. Okay, that allows us to what? Find the ciphertext, find the plaintext with a given ciphertext. And here the inverse is easy to do. It's the same as ISA. Okay, so this is their idea. Okay, so the public key including all those components of this map, which is Kn to Kn, and it is quadratic. And the secret key is just these two maps, linear maps, L1, L2. That's it. Everything else is a public. Okay? So remember, L1 does is to mix things together, L2 is the change of basis. Okay? And if you notice from the earlier definition, L2 is invertible, phi is invertible, F is invertible, every map is invertible. In this case, if you want to decrypt message, you just invert what? Invert the map one by one. And very easy to do because L2 is linear, so you can invert it easily. And F can be easily inverted because you just raise x to the t. And L1 also can be easy. So decryption process is basically invert the map 3 times. Okay? So this is it. Okay? And the toy example earlier I showed is the case you set n equal to 3 and theta equal to 2. That's the example I showed you. Okay? And the interesting about this is that once they invented the system, everybody was very excited because efficiency. It was, you can show easily. They were suggesting that n actually, the block length is actually 64 is enough. They were very excited because they were far faster than ISA. Okay? And they actually immediately submitted this one as one of the candidates for Japanese security standard. Okay, they were discussing it for several years. In 1995, right before the Japanese decide, I think the Japanese government more or less decided to accept it as a security standard. Right before that, there's a French mathematician called Perturbation. He found a way to broker the system. And what he found out is that if you have plaintext and ciphertext, here's xi's are components of plaintext, and yi's are the components of the ciphertext. And these satisfy a very special equation called a linearization equation. Okay? And we can find out easily those linearization equations by just using samples. Okay? Just plug in pairs of plaintext and ciphertext. And you can find this equation easily. And look at this equation. Suppose so this yi's are ciphertext. If you find this equation, if you have the ciphertext, if you plug in the ciphertext, what you will get is what? A set of linear equations satisfied by what? By the plaintext. That's it. You can break the system because you can have a substantial number of linear equations, linearly independent linear equations satisfied by plaintext if you are given ciphertext. So you just break it. Okay? And it's very easy to do. Okay, this happened in 1995. Okay? Okay, however, Matsumoto Ibai system, I think, is the catalyst for the development of the field of multivariable crypto system. So Pataran, as the person who broke it, immediately he and his research group developed many, many new systems which are very much inspired by Matsumoto Ibai system. Okay? And so here I want to introduce the first generation. The first generation called minus plus. Okay? So, and what does it mean by minus? Minus, which means you have a bunch of equations, you take a few of them out. Okay? You take a few components out. This is minus. And what is plus? Plus, you just add random equations to it. Very simple idea. Okay? The minus idea actually was first proposed by I.D. Shamir. Okay? It didn't work, but the idea itself originated from him. And what is S-flash? S-flash is just Matsumoto Ibai minus. And what they did is just you have a map, and you take a few components out. And then the linearization equation cannot be satisfied anymore. However, we can see easily if you take a few components out, the map is not going to be bijective anymore. Okay? But you use it for signature. It's used for authentication. You do not use it for what? You do not use it for encryption. Okay? So this is what they use. Okay? This is the last year. Yeah, in 2004, they were accepted as security standard for low-cost markets by the Information Security Technology Program of the European Commission for the New European Schemes for Signature, Integrity, and Encryption Project, called the NESI. Okay, this is last year. Okay, and the length of the signature is 249 bits. Okay, and so here, because it's a signature scheme, And to verify signature, what you essentially have to do is you have a pair of vectors. You just put them into the equation to make sure the equations are equal, if the equation is valid. If the equation is valid, then what? The signature is valid. Otherwise, you deny it. Very simple. Okay? And here, how do you sign it? To sign it is very simple, because if you keep the secret key, you know which component you take out, which means you know what is the minus you have done. What you do in order to sign a document, what you do is what? You put them back. Okay? And you randomly choose a set of values, and you can sign it easily. Okay? So this is a S-flash. Okay? So there's another generalization for encryption purpose, and this system is called HFE. HFE stands for hidden field equation. So if you look at the multimodal EMI system, the critical map is the map F, which I explained earlier, the map X, map to X to the Q to the theta plus 1. Here, Perturbation said, instead of using F like that, he proposed a new F, which looks like this, which is summation of X to the Q to the I plus Q to the J, and plus sigma summation of X Q to the I terms like that. Here, the summation index has to be small, because in this case, when you invert the map, you need to solve a polynomial equation, which can be done fast if the degree is low. Therefore, this parameter D must be relatively low. But unfortunately, Kipnis and Shamir attacked the system. They showed that if the D is too small, it's not good. Okay, so D has to satisfy some minimum requirement. Okay, and what eventually they produce is a new system, but it is secure, we believe. Actually, we believe at this stage this is one of the strongest systems, but it's very fast. Okay, however, what they did later is also very interesting. They developed something called HFE minus, which means based on FHFE, you take a few components out, you build a new signature scheme. And this signature scheme is very short. It's only have about, the system this is about 80 bits. The signature length is only 80 bits. Okay, very short, but the signing process is relatively slow. Okay, so this is the case. And later, they have further generations, and here I want to mention XL. XL stands for extended linearization attack. Okay, this is very much related with global basis attack. Okay, and there's also something new called oil vinegar, and which is for signature scheme. And then there's another new scheme called HFEV, which is a combination of HFE and the oil vinegar. So this is just examples of new scheme, which I don't want get into the details. Okay. Now I would like to start the second part. It's internal perturbation. Internal perturbation is a new idea we developed recently, and the purpose of this is to increase the security of the system and therefore increase the efficiency of the system. Okay. Okay. What is the general idea? So perturbation originally is an idea from physics. What do you mean by perturbation? So you have a continuous physical system, and often you do something called perturbation. What you do is you add a small noise. You change the system a little bit by a very small scale, such that you observe how the system reacts. So you use that trick to study the system. Okay? And what we suggest to do is to transplant this idea from a continuous system to what? To this discrete system. Okay? And this idea was first proposed in PKC 2004. And here, let me fix one thing, which is I would like to fix Q equal to 2 at the very beginning. That means the size of the small field is of 2. Okay? So in a continuous system, you can have something called a scale. In a discrete system, there's no scale. So how do you do the things like that? Okay? Our idea is very simple. We choose a small integer r. Okay? This r, and then we find a subspace, a linear subspace of linear functions. Okay? So this is z1 to zr linear functions. Okay? And we use those guys as a perturbation agent, which means I choose a small subspace and I use elements from a subspace to produce noise and add to the system. So that's the basic idea. Okay? Okay, so this is what we'll do. And we'll use this guy to produce noise. How do you do that? Okay, very simple. So if you look at this map, look at this chart, the left-hand side is the original Matsumoto Imai system. If you only look on the left-hand side, and what we suggest is you have Z1 to ZR, these are perturbation agents for a small dimensional space. And you use them to produce quadratic functions, F1 to Fn, which are decided by Zi's. And then these guys produce some noise, and you just combine these two systems together. And that's just it. That's the idea. Okay? That's the very idea. And here, how do we control the size? We control size by R, which means we do not want R to be what? Too large. We want R to be small relative to the size of n. Okay, so this is the idea. Okay, so here, that's the mathematical details. So you have the original map. You just add the f1 to fn from those space of a small dimension. Okay, so that's the basic idea, the construction. Okay, okay, and those fi's, what should I call the noise? It is a noise you add to the system. Okay, and then so I define something called perturbation set. These are something which we'll use later to do decryption. Okay, and this is a set of size q to the r elements. Okay, later we use it for decryption purpose. Okay, and then so the most important thing I want to emphasize is this r is called the perturbation dimension, which decides the size of the scale of the noise you add to the system. Okay, so let's now see what is the public key. The public key is the same. The public key is just the new what polynomials you produce, new quadratic polynomial you produce. It's the same, but the secret key. And so encryption is the same. You just plug in the values and calculate the value of the polynomial. Okay. The interesting part is the private key. The private key consists of an original map F and consists of this Z1 to ZR, which means the subspace you defined, and this points in P, which is the perturbation set, and of course the two map L1 and L2. And in the process of the decryption, you have to do a search. Okay. You have to do a search, and the search size is q to the r. Okay, you have to do a q to the I size search. Okay, one by one. Okay, and then you can use the original multimodal EMI map to find the pre-image, which means find the plain text. And here you can see that's why R must be small, because the search size is q to the R. If R is large, of course the system will be what? Very slow. Okay, so this is the basic idea of this construction. Okay, and then. Of course, once you build a new system, you always ask, what is what? Security of the system. How secure it is. Okay? And before the beginning of this year, we do not know any effective way to attack it. Okay? As I mentioned earlier, the only general way to attack a multivariable system is use something called a global basis. And global bases are general methods of solving polynomial equations. Okay? So we did some work to check how effectively global basis attack could be used to attack the perturbed cryptosystems. Okay, and in this case, we know there's global basis. Also, you have XL method. Unfortunately, in last year, in AsiaCrypt 2004, there's work done by two research groups, one in France, one in Japan. They showed that the new global basis method proposed by Forget is much more efficient than XL. Therefore, the only thing we have to worry about is global basis. So in order to answer the question, we decide to systematically analyze what is going on for this case. Okay, and you can see for our case, the system is defined more or less by two parameters. One is n, one is r. N is the original size, r is the perturbation dimension. You want to know what is the best choice of r, which means how much noise you should add such that the system is secure. Okay. And the interesting here is you realize if r equals 0, which is the original mass model in my case, we know the complexity is polynomial. But if r equal to n, which means the polynomial, I just randomly chose a polynomial. Therefore, in this case, the complexity is what? Exponential. So you have an evolution from what? In this case, very interesting. You have an evolution from polynomial to what? To exponential. And what you intend to find out is where this transition point happens, which means when the complexity starts to change from what? Polynomial to what? Exponential. Okay, so that's what we call the phase transition point. Another point we want to find out where is the saturation point, which means it turns out in terms of experiment we find out as you increase r, but up to a certain stage, when you increase r, the complexity what will stay what as the same. And this is the case, the whole system is saturated in terms of by the noise already. You don't need to add more noise. Okay, so this is the two things we're interested in finding out. And what we did is what? We used computer experiments. Okay? And the experiment is based on the F4 implementation, which is the fast global basis implementation down in Magma in Australia. We use their algorithm. Okay? And we did experiment, we time it, and also we recorded the memory, and then we discarded bad data, which means because turns out what happens here is that memory often is a problem. it's not the computing complexity. Often the program fails because we don't have enough memory. Okay, so if memory has problems, then the data is not reliable. Therefore, we delete all those points. So we derive enough data, and then we do the analysis of data. And what we found out, the interesting thing is that it seems to us when r less than 6, it's not good. If r less than 6, it stays as polynomial. And somehow when r equal to 6, the system behaves as if it's exponential. Okay? And for the r equal to 6 case, we found out the attack complexity is more or less given by this function, which is 2 to the 11.4 times 2 to the 1.16n. This is the attack complexity. From this, we realize the conclusion is that for practical use, if you want to set up the security level to be 2 to the 80 triple DS, then you want to choose r equal to 6, n equal to 100, which means you can build a system such that the block length is just 100 bits. Okay, so this is the example we will suggest for internal perturbation of mass model EMI system. However, there appeared new attacks against our system just at the beginning of this year. Okay, and the new method was developed by Professor Jacques Stern and his research group at École Supérieure in Paris. Okay, and what they did is something very interesting. They proposed differential analysis attack. Okay, so they pick up the perturbed mass model EMI system. Okay, they analyze the differential of the system. Okay, and observation is very interesting. What they did is something very interesting. Okay, they observed that if you look at differential, if you can derive a linear map, the dimension, if you treat it as a linear map, the dimension of the kernel is fixed if the noise does not do anything. If the noise does anything, then the dimension of the kernel will change. Okay, they did a computer experiment. That's what they found out. Okay, that's what we found out. And then because of that observation, what they say is that let's find out who is noise, who is not noise. And then I can denoise it. Then I can break the system. Okay? And the fundamental weakness of the original perturbed mass model EMI you realize is because the difference, if you study differentials, and if you study linear map related to differentials, the dimension of the kernel is fixed. It does not change. It stays all the time. In some way, you should understand is you have a system such that in the background it's very pure. There's no noise what? There's no noise at all. And if you add noise, somehow they can what? They can use the fact that there's no noise in the background, they can tell who is the noise. Okay? So once they know that, they realize they can denoise it. Okay? And they can break the system. Okay? Which means they develop a way to what? To attack the perturbed mass model EMI system. Okay? Using differential analysis attack. Okay? And actually, we did a very similar work independently, but we were definitely after them. Okay? And their paper actually was just accepted in AsiaCrypt 2005. Okay? It will be presented this year in May in our house in Denmark. Okay? And this sounds very bad news to us, but actually it is not that bad. Okay? First thing we observe is that because the mass model EMI system originally does not have noise, okay, whereas if I can add a little bit more noise to a system, then the method will fail because you have two noise mixing together, you cannot tell what, which noise from where. So our idea is very simple. To fix the perturbed mass model EMI system is very simple. What do? Is we add R, the number R, of randomly chosen equation to the system and mix them up and then do perturbation. Okay? Okay? And we did some experiments. Okay? The experiment shows us once you do that, actually what the differential analysis method cannot work anymore. They cannot differentiate between the noise from, in some sense, you have noise adding one noise coming from what? The new R added random equations. Another one is coming from perturbation. So in some sense, you can understand it as one noise you added horizontally, another noise you added vertically. And the differential analysis method cannot work anymore because they cannot tell which is which. So we can show that actually that their differential analysis method will not work. Okay? So this is a very good news to us. And you can see the original idea is very physical as well, right? Their attack message is denoise. And you have this idea of plus, okay? And the plus actually add additional noise to the system. And just because of that, their attack method would not work, okay? And so this is the case of PMI, okay? And this year, we did some more new work, okay? And the first one we did is called internal perturbation of hidden field equation, okay? And we basically present the way to add internal perturbation to HFE, the hidden field equation system, okay? And this was done as a joint work with Dieter Schmidt, who is a professor in the computer science department in Cincinnati. And this paper was presented at PKC 2005 in January this year in Switzerland, okay? And for this case, what really happened is that the perturbation is slightly different. And if you look at the perturbed mass model EMI system, what you did is just add the noise directly to the system, okay? But for the case of HFE, it's a little bit different. Because if you look at the original definition of HFE, HFE here. If you look at the definition of the map of HFE, and HFE is not a homogeneous map. It's not a purely quadratic map. You have linear terms. And the new idea is very simple. We will mix noise with what? With those linear terms. Instead of just add them, you somehow have a mixing going on. Okay? So that's the idea of internal perturbed HFE system. Okay? And and the difference between this idea and the original HFEV is that an HFEV is a combination of hidden field equation with oil vinegar. In this case, you can see the difference between the internal perturbed HFE and HFE is that one is kind of external perturbation, another one is what? Internal perturbation. Okay? Okay. And one more question you would ask is, how about differential analysis attack? And it's very easy to see that differential analysis attack cannot work anymore. Why? Because the HFE itself originally have noise, which means if you study the differential HFE, if you treat the difference as the differential as a linear map, the kernel, the dimensional kernel change all the time itself. It has noise. Okay? And then you will see that if even you do differential analysis, you do differential analysis, you cannot tell noise from where. You cannot tell the noise if it's noise coming from the perturbation. So therefore, the method developed by Professor Jacques Stern cannot work anymore here. Okay, for HFE case, cannot work here anymore. And the most important thing I want to mention about the internal perturbation of HFE is the computation speed. In HFE case, if you want to decrypt, you have to solve a polynomial equation. Okay, given the polynomial equation, if you have a degree, suppose the polynomial equation, suppose the degree is n. Yeah, suppose you have a polynomial degree is n. Then the complexity to solve the equation is given by such a size. It's ON3 times log of the size k bar, the big field. Okay, it's n3. Okay, the degree. Okay, and HFE is very slow. Is exactly because you have to do that. You have to solve the equation. And if you do internal perturbation, you will do a search size, which means if you do search, the size actually is, in some sense, is q to the r. Okay? And if you choose q to be 2, r is to be 2. This is what we propose. And then turns out this method in the process of decryption is much faster. It's up the size of 10 faster than HFE. Okay? And this is a result not done by us. Actually, there's a research group in Taiwan, in National University of Taiwan, in the engineering department. They implemented our algorithm. And the result they sent to us is that this method is faster compared with the similar size of HFE and internal perturbed HFE. The decryption process here is 10 times faster. Okay, so that's what they did. Okay, that's about internal perturbation of HFE, and then also in terms of solving equation itself, I think for internal polynomial is indeed much easier to implement because the degree is very low. Okay, so this is about this, and then we also did some recent work with Jason Gao here and with Dingfeng Ye and Zhiping Wu. Most of them are members at the State Key Laboratory of Information Security in Beijing, of the Academy of Science of China. And we also apply this method to something called hidden matrix cryptosystem. And hidden matrix cryptosystem was also a system developed by Pataran. And this system is based on some quadratic maps derived from matrix equations. Okay? And for this case, we also can see fairly easily that they have very strong resistance to differential attacks developed by Jack Stern, and they have also potential to be used for practical purpose. Like you can have a 121 bits implementation for this purpose as well. So this is this work is just accepted in the International Workshop on Information Hiding and Information Security, which will held in Singapore this year in May. Okay, and so this is about our most recent work, and I think that's all I have for today. And thank you very much.
Are there any questions?
So how much faster is it than RSA?
Compare which one with which?
Let's say the most efficient encryption.
In general, it's by a scale of 10.
Scale
10, yeah, in general, scale of 10. Yeah, yes.
And for the signature schemes, is
Much faster.
The verification is much faster, or?
Both cases. Both cases. And I can tell you the case for I can tell the case for S-Flash. Okay, S-Flash. S-Flash, the public key is given by 26 polynomials. Okay, 26 polynomials. Yeah, 26 polynomials with 37 variables. Okay, so that's the public.
How many bits does it take to represent it?
So the bits, the size is 26 times 37 times 36 divided by 2 bytes. Basically, that's the size of the public key. So this is about, we did the calculation, what's the size? It's about 9K bytes. Yeah, that's the public key size. So to verify the signature, what you do is you have a pair. The size of a pair is, first is 37 bytes. This is the signature. And the message size is 26. Okay? This is 26 byte. So what do you, sorry, I should write higher. So what happens here in this case? In this case, the signature size, the message size is 26 byte. Okay? Okay? And the signature size is what? 37 byte. Okay? Okay? And so from here you have 26 polynomials. Let's assume the 26 polynomials are F1 to F what? 26. To verify the signature is those 37 bytes here are the variables. Okay? And those 26 guys are putting on this side. So you plug the polynomial 37 variables into this side of the equation, and you put 26 on this side to check if the equations are equal. If you're equal, you accept it. If it's not equal, you deny it. So in this case, you can see what you have to do is evaluate the value of 26 polynomials with what? With 37 variables. And can be done very fast. Okay? Maybe here I want to mention a little bit about the fact of multiplications in finite field. If you have a small finite field, there's no multiplication anymore. What you do, because you can do exponential, you can do adding and such. So you can make it much faster. Yeah, there's no more multiplication. Basically, you have to do addition and a search. So that's the idea. Yes. Yes.
One of your systems that you talked about had an 80-bit signature, you said.
Yes.
Isn't that so short that you could do a
Search.
birthday,
No, it's not
tag on
easy. No, not so easy. Right. It's not so easy. It's not so easy. So maybe 80s is actually is around the 80s. So the signature size is around the 80s, right? Which means the possibility of the signature is 2 to the 80s. For birth attack, for this case, not so easy.
Okay.
Yeah, it's not. Maybe it's maybe 87 or 80 something like that. Not exactly 80.
Okay.
Yeah, and the reason I want to mention is because in the new European security standards, at the very beginning, when they set up a standard, it's any algorithm they will accept to look at it. They will look at it only if you can show at this stage the security is at 2 to the 81 triple DES. Okay, that's what they consider as to be secure. Yeah, if you have any algorithm, if you have any system, you can break. If you can break it with less than 2 to the 80 triple DES, they will not even consider it. So the 80 is always kind of here at this stage. The 80 is the number they consider. So that's yeah, it's around. I mean, it's not around the 80. They're higher than 80, maybe 87 or something like that. Yes.
Okay. Any other questions? Okay. Then let us thank our speaker.